Good morning, everyone. Let's start. So I've shared in Google Classroom, I've already shared a couple of recorded videos on the probability basics that we will use in this course. A lot of it dealt with some basic concentration inequalities, Markov's, Chebyshev, and Chernoff bounds, and also sequences of random variables. And we'll be using this extensively in the course. So I expect you to be familiar with those. You may have seen this, some of you may have seen this in a probability course previously, but in case you have not seen it, then it's a good thing to know. Okay, so first I'll maybe check if there are any questions regarding those topics. And then today after that we will start with the core concepts of information theory. So today I'll start by talking about data compression. How do you model the problem of data compression? What do you say is a good solution for the data compression problem? And while we will not go into the algorithms or optimal algorithms for compression of sequences, we'll at least see what we mean by a good solution to the data compression problem. Okay, so in the recorded videos I shared, there were a couple of inequalities along with proofs. The first was Markov's inequality, which says that if x is a non-negative random variable with a finite mean, then this bound always holds. The probability that x is greater than or equal to a is less than or equal to mu over a. And we saw this in the last class as well. And this was used to prove the Chebyshev inequality, which holds for general random variables, not just non-negative random variables. As long as the random variable has a finite mean and finite variance, the probability that x deviates from the mean by an amount a is upper bounded by sigma square divided by a square. Now, in certain applications, this is good enough, but sometimes we need tighter bounds. This bound is generally loose, and therefore we sort of one of the best known bounds is the so-called Chernoff bound, which says that the probability that x deviates from the mean by an amount a is given by this complicated looking expression. Now, the Chernoff bound is one of the tightest, but unfortunately, it is also pretty difficult to use in practice because as you can see, it's a complicated expression. It's a function of, you have to minimize this moment generating function over all possible t. And so getting a closed form expression in many applications is hard. But but at least for certain random variables, you can obtain an upper bound on this particular quantity. So for example, if you have a sequence of IID random variables, which are all Bernoulli P, then this quantity, the probability that 1 over n summation xi, so this deviates from p by an amount delta, is upper bounded by this simple expression. So this is sort of what I call the simplified Chernoff bound for Bernoulli random variables. So in many cases, for example, in this particular course, this expression is more than sufficient for many of the problems that we will try to solve. So we'll try to bring in Bernoulli random variables into our problem as much as possible, and even though our original problem does not involve Bernoulli random variables, we'll try to bring in Bernoulli random variables and try to use this particular bound. Okay, we'll see some applications of some of these bounds soon. So, but are there any questions regarding these topics, regarding the proofs of any of these bounds? Any questions?
Sir.
Yes, yes, sir.
Sir, in one of this topics, like a sequence of random variables, there you had said this like probability of this 1 by n sigma xi greater than or equal to alpha,
Okay.
that's less than mu x1 by a, because like xi is for all xi is like their IID, no? So you had
Sorry, can you check this? Yes. So what would be the probability?
probability of
1 over n.
1 over n, like summation I equals
Uh-huh.
1 to n xi
Yes.
is greater than or equal to a.
Mm-hmm.
So this probability, close bracket,
Yeah.
so this is less than or equal to uh, like that expectation of y by a. Like you had taken this y as this first term, 1 by n sigma of xi.
Okay. So this is y. So whatever is the probability that y is greater than or equal to a?
Is
Yes.
less than or equal to
Mhm.
expectation of y by a.
Yes. So this is the Markov's inequality.
So based on this, you said one more, like where you take the LHS, like probability of you don't take 1 by n, you
Mhm.
take only the summation. Uh,
Okay. So in that case, you multiply both sides by n and then use that directly.
so I didn't understand how that RHS in that inequality RHS it's mu by NA. That
Mu
yes.
by na. Okay. So okay. So maybe there was an error in the video. I'm not sure. So let's do this. So I equal to 1 to n. Xi is greater than or equal to a. So this would be less than, of course, this is the expectation of y by a. What is the expectation of y?
Mu x1. Uh,
Correct. So it is 1 over n times the expectation of summation I equal to 1 to n xi divided by a. So the expectation can go inside. So it is 1 over n summation I equal to 1 to n expectation of xi divided by a. So if all of them are IID and the expectation of xi is equal to mu, then this would just be equal to mu over a.
okay, okay, sir. So in the RHS when we don't have this 1 by n.
Uh-huh.
Oh, okay, okay, sir.
Right.
Got it. Uh,
So it depends. So that is why this bound is typically weak. Uh, so so for example, if instead if I had let's look at probability 1 over n times summation I equal to 1 to n xi, uh, let's say minus mu is greater than or equal to alpha. So note that this is summation. So we're looking at the random variable y, which is 1 over n summation I going from 1 through n of xi. Okay. And the Markov's inequality tells us that this is less than or equal to mu divided by a. So let's assume that a is some constant which is independent of n. So this upper bound that we obtain is also independent of n. So it's not a function of n. So let us try something similar. Of course, it's not exactly the same thing, although you can bring it to the same form. But let us try to do the same, but using Chebyshev's inequality. Okay, it's the same quantity. The basic random variable is still the same. It is 1 over n summation I going from 1 through n of xi. Right. So this, as we know, is less than or equal to the variance of y divided by a square, or in this case alpha square. Right. But now what is the variance of y? To n xi divided by alpha square. So what is the variance of this particular quantity? Let's assume that all the xi's are IID and they have mean mu and variance sigma square.
So xi minus mu whole square.
Sure.
Sigma square by n square.
Correct. Sigma square by n square. Are you sure? So variance is just this, right? So it is 1 over n. Okay. So what is the variance of 1 over n times summation I equal to 1 through n? It is 1 over n square summation I equal to 1 to n variance of xi, right? And as someone kind of pointed out, it is, what is summation of the variance? It is just n times sigma square divided by alpha square. Is this clear? So we're looking at the variance of y, which is the variance of 1 over n times summation I going from 1 through n of xi, right? So the variance of some constant times a random variable is that constant squared times the variance of that random variable, right? So it's 1 over n squared times the variance of the summation I going from 1 through n of xi, right? And the variance of the summation of IID random variables is basically equal to the sum of the variances, correct?
Sir, actually in the video you had given it as like variance of x1 by a square. I think that n was missed out.
The variance of xn by
You took
a
1 by
square.
n square, no sir. Actually, in the video you have taken 1 by n into n sigma square.
Okay. So maybe there was a mistake over there. Not sure.
Okay, thank you, sir.
Okay. So here, so therefore, what is the variable? So this is equal to sigma square divided by n times alpha square, right? So as n tends to infinity, we see that this quantity tends to 0. 0 as n tends to infinity, right? So basically, if you take a large number of random variables, sum it and normalize it, then with very high probability, as n tends to infinity, this quantity y is going to tend to mu, right? And that is indeed what the weak law of large numbers says, right? So later on I talk about the weak law of large numbers, which says that if you have any sequence of IID random variables with finite mean and finite variance, then the limit as n tends to infinity of this probability, the probability that 1 over n summation I going from 1 through n xi deviates from mu by an amount epsilon. So this, in the limit, this is equal to 0. Right? And that is, it's just a consequence of Chebyshev's inequality. Right? Okay. So what does this basically tell us? So this is a consequence of the weak law of large numbers. This is a consequence of this is the weak law of large numbers. So 1 over n summation I going from 1 through n xi minus is very, very close to mu as n tends to infinity. Right? Any questions? Let's do a simple example. Right, and this example has to do with the geometry.
Sir?
Yes.
So that weak law of large numbers, that limit you took now, sir. So what is the, the significance? I didn't get that much clarity. Like we're taking that, like average of those random variables.
Correct.
We are taking, we're subtracting the mean from it. And so
Correct.
it's like the difference between that quantity and the mean is very less. So
Correct. So
that is what we are trying to.
yeah. So okay. So let's take what do we say? So common intuition or common practice. So when we say that I toss I toss a fair coin a number of times, we know intuitively that roughly the number of heads I'm going to get is roughly equal to the number of tails, right? So it's 50-50 chance. So when I count the number of heads, what exactly am I doing? So let's take any coin. It could be a fair coin or it could be a biased coin. When I toss the number of heads, when I toss the coin, say n times, and I count the number of heads, what is it that I'm counting? I'm basically counting this, right? So if I take xi to be equal to 1 if it is a head and 0 if it is a tail, then basically summation I equal to 1 to n xi is basically just counts the number of heads I have got in those n tosses. And 1 over n times the summation is basically the fraction of times I see a head, right? Fraction of time you get a head, right? But what is mu in this case? It is the probability of getting a head, right? So mu is the expectation of xi, right? Which is what? What is expectation of xi equal to?
So x into probability of x. So here head means like
Correct.
1 into half.
Correct. So 1 into the probability of a head plus 0 into probability of tail, correct? Which is just probability of getting head, right? So this is nothing but, so mu is the actual probability of getting ahead, right? So this is the actual bias of the coin. If it's an unbiased coin, then P of H equal to half. If it is not exactly biased, sorry, if it is not unbiased, then this is exactly equal to the probability of the head. So what is this? So this is sort of the empirical frequency of getting ahead, or the empirical average, right? Whereas this is the true average, the true expectation. And what the weak law of large numbers says is that if at least if the sequence is IID and these technical conditions are satisfied, then this empirical average always converges to the true average and it converges in this particular sense.
So can you repeat in which case it converges?
So if all the if xn is a sequence of if it is an IID sequence, and if these two conditions are satisfied, then this convergence holds.
Okay, sir.
Right?
So
So
it's
the empirical average converges to the true average. Right? So this is a sequence of random variables. Correct? This is a random variable basically. Right? 1 over n summation I going from 1 through n of xi is a random quantity. Whereas this is a deterministic quantity. Right? Mu is a number. It's some number depending on the probability distribution. Right? And basically what we're saying is that as n tends to infinity, the empirical average converges to the true average. So this is, so 1 over n summation I equal to 1 to n of xi. So this is the empirical average. Whereas mu is the true average, also called the ensemble average. And the weak law of large numbers says that if you have an IID sequence with finite mean, then the empirical average always converges to the true average. But now it depends on what you mean by convergence, right? If you have a sequence of numbers, then there is a particular sense where you can define convergence. Whereas for random variables, there are different notions of convergence. And this is one particular notion, that is the limit as n tends to infinity of this quantity is equal to 0 for every epsilon greater than 0. And this is called convergence in probability. There are other notions of convergence as well. And in fact, the weak law of large numbers holds even if you just have a finite mean. Even if the variance is not finite, this still holds as long as it's an IID sequence. But then the proof becomes simpler if you have a finite variance.
okay. Thank you, sir.
Okay. Yeah. So similarly, there's also a strong law of large numbers. If you have seen it before, and basically what it says is under the same conditions, you can prove that the probability of the limit as n tends to infinity summation I equal to 1 to n xi 1 over n xi minus mu, this quantity is greater than epsilon is equal to 0. So note that here the limit is outside the probability, whereas here the limit is inside the probability. This is the strong law of large numbers. We don't really need it in this particular course, but as it turns out, this is a stronger notion of convergence. This is another notion of convergence, and for IID random variables, even this law holds. In certain applications, you need this, but for many applications, just the weak law of large numbers is enough. This is just extra information. Any questions? Okay, so let's see an application of whatever the weak law of large numbers, or or even Chebyshev's inequality in some sense. So let's look at the geometry of uh, of Gaussian random vectors or Gaussian random variables. Gaussian RV in high dimensions. Right. So this is a very useful thing to know, and it arises in many problems, including machine learning, information theory, and so on. So if you look at the one-dimensional Gaussian random variable, the PDF is, as you all know, it's a bell-shaped curve, right? So it looks, so the Gaussian random variable with zero mean and finite variance looks something like this. Right? Okay, it looks a bit skewed because of my drawing, but let's assume that this is symmetric about uh, the y-axis, right? So this is x, this is the PDF fx of x, right? So as we see, this a lot of the probability is concentrated around zero, and the farther away you go from zero, the probability of getting an x reduces, right? Now the question is, what happens in very high dimensions? Let us assume that I take a random vector. Recall that all vectors are going to be indicated in the following form. So x superscript n tells me that it is an n-dimensional vector. Right? It has n components, and I sometimes write it as x1, comma x2, comma dot 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 up to xn. So it's an n-dimensional vector where each xi, let's assume that each xi is Gaussian. So Gaussian is this calligraphic n with zero mean and variance sigma square. Okay, so they're all IID, which implies that all the xi's are independent of each other. The random variables are independent, and all of them follow the same distribution, which is basically this Gaussian distribution. Okay, so now if it is a very high dimensional Gaussian, then where does most of the probability lie, right? So as we know, well, a lot of the probability in for a one-dimensional Gaussian, most of the probability lies in this particular interval, right? Between some quantity alpha minus alpha to alpha. Right? So we can say that much of the probability lies in this particular interval. Right? Even if you take a two-dimensional Gaussian, now if you go to two dimensions, you'll see that it's going to be a bell-shaped curve. It's really going to look like a bell, right? And a lot of the probability is going to lie within some circular region. Right, a lot of the probability is going to lie within some circular region. Okay, but as it turns out, if you look at very high dimensional Gaussians, that is for very large n, most of the probability in fact lies in a rather more peculiar region. It lies in a thin shell. So what do I mean by that? So much of the probability is going to be concentrated in in some region which looks like this. Of course, we can't really visualize what is happening in very high dimensions, but it's going to be, a lot of it is going to look is so a lot of the probability is going to be concentrated in a region which looks like this shaded region. Right, it's a shell which is basically lies in the intersection of two of outside one ball but inside another ball. Right. So one way to say that is, so in other words, this is going to be a ball of radius r, let's say r plus epsilon, and this is a ball of radius r minus epsilon, and a lot of the probability is going to lie in this particular region. It's between a ball of radius r minus epsilon and another ball of radius r plus epsilon. Okay, but again, I'm drawing it in 2 dimensions, but in fact this holds only for a very high dimensional space. So as for n very large, right? But obviously I can't draw it here. So what is it? So what is the formal statement I'm trying to make? So xn lies in a in this particular shell. So in other words, the norm, or the norm squared, is going to be between something into 1 plus epsilon and something into 1 minus epsilon. So can you say what the radius of this ball would be? So it is some constant alpha and alpha. So it's going to lie between two balls, a ball of radius whatever square root alpha into 1 minus epsilon, and another ball of radius square root alpha into 1 plus epsilon. Any guesses what this alpha should be?
Maybe the mean of the the mean along the one dimension.
I'm sorry, I can't really hear your voice.
So, sir, I was saying maybe the mean along one dimension.
The mean, well, they're all zero mean random variables, right?
Okay. Oh. Right, sir.
So it may help to sort of expand out the norm squared. What is that equal to? What is it equal to?
X1 square plus X2 square.
Correct. So it's x1 square plus x2 square up to xn square, or summation I going from 1 through n of xi square. Correct. So now looking at these, you know that all the xi's are IID random variables, zero mean variance sigma square, Gaussian. So now what do you expect this to be? As n tends to infinity, this will be close to something. What will it be close to?
So can you repeat? Yes.
So this is the norm, right? The norm squared, correct? I'm claiming that for very large n, this will be very close to a certain number. What will that number be?
N sigma squared?
Correct. So it's going to be n sigma square, right? Because if you look at the expectation, the expected value of the two norms squared, this is going to be n times sigma square. So what we would expect, or what we would intuitively, it should feel that this squared should be between n sigma square into 1 plus epsilon and n sigma square into 1 minus epsilon. Correct? Or what I'm trying to say is that the probability that norm xn square minus n sigma square is greater than or equal to n sigma square epsilon. So this probability tends to 0 as n tends to infinity. All right. So is this statement clear? So if you look at the norm of xn, right? So in other words, we're looking at it, think of looking at xn in polar coordinates, right? So where does most of the probability lie? So you look at whatever r, theta, phi, whatever, theta 1, theta 2, up to so on. But what you're really interested in is only the norm, right? And this statement says that the norm is going to be very close to n times sigma square, or the norm squared is going to be very close to n times sigma square, which means that with very high probability, it's going to lie in a very thin strip or a thin shell.
Sir, can you please repeat that again?
Okay, so just look at this particular expression. Okay, so look at the set of all vectors. So try to think about the following statement. Look at the set of all n-dimensional vectors xn for which the norm of xn is between some whatever alpha 1 and alpha 2. Okay, all vectors. So the set of all possible xn which satisfies norm of xn is greater than or equal to alpha 1 and less than or equal to alpha 2. Right? So let's even break that down. So the set of all possible xn such that norm of xn to norm of xn is less than or equal to alpha 2. What is this set? What does this set look like?
Inside of a sphere.
Exactly, it's going to be basically a ball, right? It's going to be an n-dimensional ball of what radius? What is the center? What is the radius?
Center 0, radius alpha 2.
Correct. So the center is 0 and the radius is alpha 2. Good. Okay. So now let us look at the set of all possible xn such that norm of xn is greater than or equal to alpha 1 or some other number alpha 1. Alpha 1 is less than alpha 2. What does this look like?
Smaller ball with radius
Correct. What
alpha.
is the region? Is it the inside of a ball?
Inside the sphere.
Outside
Is it-
alpha.
And above alpha, sorry.
It's outside alpha 2, right? So this first set, let's, oops. So this is set A. So this is this region basically. And now let us look at set B, which is this region. So this radius is alpha 2 and the region is the region B is the region shaded in blue, which is the outside of this entire ball. Right? So the set of all xn for which the norm of xn is greater than or equal to alpha 1 and less than or equal to alpha 2, what is that region going to be? It's going to be the intersection of these two, right? Which is basically this. All right. So the radius is greater than alpha 2 but less than alpha 1. Sorry, it's going to be greater than or equal to alpha 1 but less than or equal to alpha 2. So it's the region shaded in green. Correct? So this is what I call a shell. Right? So this is of course in 2 dimensions, but think about it in n dimensions. Right? Similarly, you have an n-dimensional ball, which is basically the set of all xn, where the norm of xn is less than or equal to alpha 2, and xn such that the norm of xn is greater than or equal to alpha 1. So the intersection of these two is going to be this. We think about it like a shell, but in much higher dimensions, and that is what I call this shell. In n dimensions. So this is what it will look like in 2 dimensions. You can similarly visualize it for 3 dimensions, right? You have a ball, you have another ball inside it. The region between these 2 balls corresponds to this shell, right? And you can generalize it for general n dimensions, right? So the inside is hollow, so it's hollow inside, but then you have this one smaller ball sitting inside the bigger ball. Okay. Now the claim is that what this particular claim says is that if you look at an n-dimensional Gaussian, then most of the if you pick a random n-dimensional Gaussian vector with IID components, then with very high probability it is going to lie in a shell. Right? The probability that the random variable that you draw or the random vector that you draw is going to lie in a shell is going to be very, very high. And what is this shell? This shell has inner radius alpha 1 equal to n sigma square into 1 minus epsilon, and outer radius n sigma square into 1 plus epsilon. Sorry, square root of this. Right? So xn, so this is the shell n sigma square into 1 plus epsilon and square root n sigma square into 1 minus epsilon. This is another shell, right? This is the outer radius, and this is the inner radius. The outer radius is what I called alpha 2, and the inner radius so for large n, the random vector which is Gaussian with IID components, with IID Gaussian components, so that is going to lie in this particular set with very high probability. So the probability, so if I call this a shell with inner radius alpha 1 and outer radius alpha 2, then the probability that a randomly drawn xn does not lie in the shell n sigma square into 1 minus epsilon sigma square into 1 plus epsilon. This tends to 0 as n tends to infinity. In fact, you can say that this is certainly less than or equal to some constant divided by n. Is this statement clear? So in particular, what it says is that if you try to visualize a Gaussian random vector in very high dimensions, then the probability that it is close to zero, that you'll get a quantity which is very close to zero, is actually small, right? In one dimension, if you look at a one-dimensional Gaussian random variable, you see that it's going to lie somewhere between minus alpha to alpha. It somehow looks like, since the bell is maximum at zero, one may think that with very high probability you're going to get some number close to zero. But on the other hand, if you, in very high dimensions, something more peculiar happens, and that is the probability of getting a vector, of drawing a vector very close to zero, is actually very small, and very far away from zero is also very small. In fact, most of the probability lies in this very, very thin shell, right? And in fact, it turns out that if you look at the volume of a ball, if you look at an n-dimensional ball, most of the volume is also concentrated in this very thin shell. Okay, but yeah, but is this statement clear? So this is a picture to keep in mind, although although we can visualize it only in 2 dimensions. Yes.
So this bell-shaped Gaussian random variable which we are taking,
Yes.
so there's one dimension. So just to visualize, like if I consider 2 dimension,
Correct.
then I can consider it like the actual mountain.
Correct. It's going to look like a mountain, which is true.
And what you have drawn here is like the aerial view of a mountain, where I am
Correct,
drawing
exactly.
2 concentric circles.
Exactly.
So the most of the mass or the volume of the mountain would lie like it will be like from maximum will be in the middle, and as it moves away from the peak of the mountain, it should decrease. And what you're saying is actually something reverse, no sir?
That it lies in a thin shell, right? So that seems very, very counterintuitive. That's correct.
uh, um,
The reason why this seems so counterintuitive, now obviously it is true that if you look at even an n-dimensional Gaussian, if you look at the probability density function, if you just look at the value of the probability density function, then obviously the PDF is going to be maximum at zero, right? That's just by definition of the Gaussian PDF, correct?
yes sir.
But on the other hand, what matters is not the value of the PDF, but where most of the probability lies, right? So what is the set where, in some sense, most of the volume lies? Okay, so let's break this into 2 steps. So step 1, is it intuitive that most of the probability is going to lie within some ball, not a shell, but a ball?
Yeah, that's what we expect.
Correct. That's what is expected, and that is something which is intuitive, right? So even in very high dimensions, you would expect most of the probability to lie within some particular ball, and the ball in particular could have radius square root of n sigma square into 1 plus epsilon. Correct. If I had said that, okay, with very high probability is going to lie within this ball, then that is something which seems intuitive, because after all it's a bell-shaped curve. So the probability that it lies outside this is going to be small. What is counterintuitive is that it's not just outside this ball. Even if I take a shell, actually a very, very thin shell, even then the probability of seeing something is small, right? And the reason why that is happening is because if you go to very high dimensions, you look at the radius of a ball of radius r1. Yeah. So the reason why this is happening is because in high dimensions, that is for large n, you look at a ball. This is how I define a ball of centered at 0 and with radius r. You look at the set where most of the volume of this ball lies. It in fact lies very close to the surface. The interior actually contains very little volume, which seems counterintuitive because we can only visualize in 2 and 3 dimensions, and in 2 and 3 dimensions much of the area is actually in the center, as it seems. But in fact, for very high dimensional balls, the most of the volume of the ball in fact lies in this particular region, in a thin shell. So if you look at the volume of a ball of radius r, this turns out to be roughly the same as the volume of a shell with inner radius r into 1 minus epsilon and r. And this is a peculiar fact about high dimensional spaces or high dimensional balls.
Okay, so this is not applicable for n equals 1, 2, or
No,
those.
it is not. It is not for n equal to 1 or 2 or small n. It is very particular for very large n. And that is the statement over here, right? It is the only statement that we're trying to make is for large n. And that is really where we'll be focusing on for much of this course. So it is for, so we'll mostly be interested with large and with large number of samples in high dimensional spaces, because that is where this phenomena of concentration of measure happens. So a lot of the mass is concentrated in very small sets. So for example, for the Gaussian, it is going to, much of it is concentrated in this shell. Okay. And the proof of this is very simple. You just look, this statement is the same as this particular statement, and you can just prove this using Chebyshev's inequality, right? So this probability is less than or equal to the variance of norm xn square divided by n sigma square epsilon, and you can just bound this fairly easily, right? Or maybe a better way to write this is, maybe I shouldn't have put it in this particular form. So 1 over n of this minus sigma square greater than or equal to sigma square epsilon. So then I can write it in this particular fashion, divided by sigma square epsilon. So this just turns out to be equal to 1 over n square sigma square epsilon times the variance of x1 squared, and this is some constant divided by n. So as n tends to infinity, this quantity tends to 0. Okay. Any questions? So this is just Chebyshev inequality, and even Chebyshev's inequality tells us what the geometry of a high dimensional Gaussian looks like. And to see why this is the case, so for example, for this statement, you can simply, here's a simple homework. So the volume of a ball of radius r turns out to be equal to this quantity. So it is pi raised to n gamma n by 2 has 1, pi raised to n by 2 gamma n by 2 plus 1 r to the n. Right, where this is the gamma function. So if you sort of substitute this, and this volume is basically this minus pi raised to n by 2 by gamma n by 2 plus 1 r into 1 minus epsilon whole raised to the n. So this is the volume of an n-dimensional ball, whereas this is the volume of this is the volume of this particular the inner ball. So the volume of the shell is the volume of the outer ball minus the volume of the inner ball, and this you can show is approximately equal to pi raised to n by 2 gamma n by 2 plus 1 r to the n.
Sir, what was beta? I didn't get it.
Beta is some constant which does not depend on n. So in this particular case,
Okay.
it is going to be the variance of x1 square, which you can calculate. It turns out to be just, I think, 3 sigma square divided by, sorry, I think it's going to be 2 sigma square or something, divided by n square epsilon. So this is the fourth moment. This turns out to be the fourth moment of x. Okay, so let's stop at this point, since we're out of time. But if you have any questions, then I can address them.
Thank you, sir.
Any questions? Okay, so if not, we'll meet in the next class. So see you then.